So today, I'd like to discuss with you domain and range. Okay? Now, you may have some ideas about domain and range from last year. I think you did a little bit with that in Algebra 2. But we're going to start with some definitions and then just get right into it, I guess. The domain of a function is the, we'll say it this way, largest possible set of inputs that will yield an output. That's one way to say it. The domain is the largest possible set of inputs that will yield an output. And it's important to say when we're talking about domain and range for functions. Okay, we're not going to talk about anything else today. Just things that are functions. Okay. We could, if we wanted to, replace a part of this definition. Here's another way to say this. We could say, or it is the largest possible set of inputs for which the function is defined. What does this basically mean? That we're trying to think of all the possible numbers we can plug into our function and get back an answer. Okay, that's what we're really talking about. Okay? All right. Let's discuss range. Range is the set of all possible outputs. Or another way to put it, it's the set of y values. And by now, I want you to think, when you hear the word y values, think of outputs. They're like synonyms. That a function attains. In other words, I take all the numbers I think of in the domain. I plug them into the function. What kind of outputs am I getting back? What can you say about them? What are all the outputs that we're getting back? And that's what range is. Okay, so these are two pretty straightforward definitions. And each problem can be kind of fun. You never know. It could end up being surprisingly easy or a little more complicated. All right, so let's start with an example. So suppose I tell you f of x equals something like this, 3x plus 7. And we want to talk about what the domain is. So I'm just going to let D be the domain. The question is, what x values can we plug into that function and get something back? Any number we want, actually. Anything we plug in will be okay to multiply by 3. We could add 7. Everything would be fine. So negative infinity to infinity. We can do that. Okay? Let's talk about range. Okay, so range sometimes can be a little difficult. Not in this case, though. What kind of y values can we get back? So I'll ask you a question. Could I get some really big y values back? Sure I could, right? If I plug in a really big x value, get back a really big y value. Right? Can I get numbers that are very negative? Can I get like negative 1,000,000 back if I wanted to? Sure. As a matter of fact, I can get back any number we want. Okay? You can see that on a graph pretty easily. Sometimes it's nice to look at a graph. Y equals 3x plus 7. We start at 7 on the y-axis, up 3 over 1, up 3 over 1, down 3, back 1. We end up getting a line that looks something like that. And here's what you know. No matter what x value you pick, on the x-axis, there's a y value on the graph that goes with it. And that's true anywhere you go. So if you go over here and you pick a different x, we'll call that x2 maybe, and we have to look down, but if we look down, yep, there's a point on the graph, and there's the y value that goes with it. Okay? So every point along the x-axis has a y value to go with it. The question is, when we write domain and range, basically how do I want you to write it? This is interval notation. This means go from the lowest possible number you could dream of to the highest possible number you could dream of. And you want to say it that way. You could write this. You could write, it looks like that. It's like the letter R, but with a line behind it. That means all real numbers. You can do that if you want as a way to represent the domain and range. Okay. All right, let's look at one that's more interesting, because that problem wasn't very difficult to do. So function f of x equals the square root of x minus 2. So you should ask yourself, what x values can we sub in and get back real y values? When I say real, we want real numbers. We're not going to have any complex numbers as results. Okay. So some of us may know this. The way to do this, start thinking to yourself, okay, could I plug in 0, for example? No, because if I plug in 0, 0 minus 2 is negative 2. Square root of something negative 2 is not a real number. But I can plug in 2, interestingly enough, so 2 is going to get included. And then anything bigger than 2 will work. Okay, let's talk about range. What kind of numbers will we get back? This is the next question. We plug in those answers. When we start taking the square root of those numbers, what do we get back? You agree, James? Do you agree with all real numbers, or no? What do you think? All non-negative numbers. That's a new word, non-negative. Non-negative means numbers that aren't negative, so anything that's positive plus 0 can be included in that set. And let's think about that. If we plug 2 in, 2 minus 2 is 0, right? Rad of 0, 0. So 0 is definitely a possible answer to get back. There's no way to get anything negative, because we talked about this. The square root symbol means return the positive number, right? Only. The positive square root of whatever's underneath this radical. Okay? And then we can get anything back. We can get a really big number if we want by plugging in huge numbers for x. So if you plugged in something like this, you subtracted 2 and took the square root, sure, that would be fine. Right? You'd get an answer. It would get bigger and bigger and bigger. Okay? So that's a little bit more interesting. All right, let's try one more, or at least a couple more. So suppose f of x equals this function, 3x plus 5 over 6 plus x. Okay. So now I ask the same question again. What's the domain? What's the range? I'll give you a minute or two to think about it. So let's talk about domain. There's an x value now that won't have a output to go with it. That's right. So we just got to talk about how you write that. Would numbers that are very negative work, like negative a million, things like that? Sure. So we can start down at negative infinity. We can go all the way to negative 6, but we can't include it. So we put a parenthesis around it. This is called interval notation, which I briefly discussed, but I'm reviewing it with you. All right? And then we put a little u, and the u means union. That means that we can do this first set here, and then whatever set I'm going to write over here. Well, anything bigger than negative 6 works, so we write negative 6, comma infinity. So these are all the x values we're allowed to sub in to this function. Okay? Let's talk about y values. Do we get back every possible y value? What do you think? Yep. Yep. What don't you get back? Okay, I got to vote that you can't get 3 back. All right. So anyone else have believe that you can't get 3 back? You're not sure? Not sure? Okay. First off, I want to test this out. For some reason, magically, we've been told that this function can never be 3. So I'm actually going to see if that's true. So let's actually take this function and set it equal to 3. So I'm going to write 3 equals 3x plus 5 over 6 plus x. And what we want to try and do now is solve it. We're going to see, is it possible when y is 3 that, that x could be something? If that were the case, then 3 is on the graph. Let's see what happens. All right? I guess we'll cross multiply. That's probably what a lot of you would do, or something like that. Multiply through by the common denominator. I prefer you say it that way. So 3x plus 5 times 1 equals 3 times 6 plus x. Okay? 3x plus 5 equals 18 plus 3x. And I claim that's kind of a weird equation, isn't it? You subtract 3x from both sides, and you end up getting 5 equals 18. Well, that doesn't make any sense, right? When you get a statement like this, where they're saying two things are equal and clearly not, that's called a contradiction. And if you have a contradiction, what that means is somewhere you assume something incorrectly, or you wrote something down on the board that's not true. So that means that this statement is not true, which implies that y never equals 3. Okay? So now the question is, how do you figure that out? Do some reverse algebra? There you go. Okay. Fine. That'll do it. There's a couple of ways to do it, but here's what I'm thinking. Let's take the original function. I think I wrote it as f of x equals 3x plus 5 over 6 plus x. And we're going to write it this way. We're going to say y equals 3x plus 5 over 6 plus x. And what we're going to attempt to do now is we're going to try and get x alone. So let's try and do that. If we're going to get x alone, we're going to multiply through by the common denominator. So we'll get 6 plus x times y equals 3x plus 5. Right? And let's keep track of our goal. Our goal is going to be to try and get this to look like x equals. All right. So what can we do? I'm going to distribute the y here. So I get 6y plus xy equals 3x plus 5. And if I look carefully, I see two x terms. Here's an x term and here's an x term. I'd like to get them together on one side and get the non-x terms on the other. That turns out to be a very handy way to solve equations. That you're looking for particular variables in two locations, get them both to the same side. So watch, I'm going to do 6y minus 5 equals 3x minus x times y. James, you do it this way? Or not really? Okay, so we'll talk about the other way in a minute. Okay? So you'll notice if we look on the right side of this equation, here's the variable I'm trying to solve for. I'm going to factor it out. I get x times 3 minus y equals 6y minus 5. And then we finish by dividing by 3 minus y. Okay, take a look at that expression, and what do you notice? Y can't equal 3. So this is a way to figure out range algebraically. Pretty slick, right? So we should finish off by saying that the range is negative infinity to 3, not including 3, union 3 to infinity.